Okay, animals. Oh, wait. Hold on. Am I gonna get freaking signed out of this thing? We're in dangerous territory. Okay, I think I'm good. Okay. Answer a few questions. To be sure you've gotten this before we move on. You're studying the characteristics of an animal and learn that it is a thermoregulator. Which of the following is a valid inference about this animal? Uh, it will not survive if its body temperature differs substantially from the set point for an extended period of time. I would assume it's this. Yeah. Okay. These graphs display data for two variables. It's a conformer. Wait, what? Wait, I think it's a conformer for. Um, but if the water concentration goes up, but the blood concentration stays the same, then it's regulating. It's a regulator for this and a conformer for blood temperature. Yeah. Um, Many animals are regulators for the blood concentration of sodium ions. For these animals, select the which of these variables is likely to change according to environmental conditions. I don't know if this amount, but this and this one shouldn't be this. Yeah. Oh, there is. Then I would say, then I guess it's intake of dietary. An animal is a regulator for the blood concentration of both sodium ions and chloride ions. Which of the following is a valid inference about this animal? The animal would increase excretion in the urine if the blood concentration of these ions increase above the set point. Yeah. Okay, that was pretty easy. If an organism is an osmoregulator, which of the following is a valid inference about the animal? Show work. What the hell? Definitions. Okay, next. Osmoregulation and excretion are I mean, I would say that's true. Chemical processes. I actually don't remember this. I would imagine that they can't stop during torpor. Do I have torpor? What the fuck is that? Torpor. What a terrible word. What an awful word. Oh yeah, I guess I was only thinking about excretion. Yeah, I don't know why I didn't put that one at the beginning. The force driving simple diffusion is the concentration gradient. Well, an energy source that drives active transport is ATP. Which of the following processes must freshwater fish undertake to maintain homeostasis? So freshwater fish are lacking it or need to pee a lot. Which of the following animals generally has the lowest volume of urine production? Definitely not freshwater fish. A marine fish, probably. I would honestly guess it's this. Because I think bats. Wait, hold on. Ugh, God, that is disgusting. I'm just playing. Yeah, what the? It's either that or this. I feel like what the freshwater flatworm. Wait. Freshwater fish? No. Marine fish or vampire bat? Okay, I'm just gonna fucking check. Because I thought that those were the ones that do uric acid production. All right, let's do marine bony fish. Okay, so it wasn't even about urea or whatever. Which of the following best explains the death of a marine sea star that has been mistakenly placed in fresh water? Oh, that's interesting. So marine needs to drink a lot of water. And if you drink a lot of it was so hyperosmotic to the fresh water that it could not osmoregulate. Wait, actually, let's think about that. What happens? So a sea star that's marine has like one, what is it called? 1/3 osmolal, and it's drinking a lot of water and it's getting rid of salt really fast. When you put it in the fresh water and it does the same thing, then it's going to become it's going to drink a lot of water, but it's not going to get any salt, but it's going to get rid of the salt. Which means it should become hypotonic, no? Because what is the water going to diffuse? The water is going to diffuse into the cell. I mean, this one seems kind of possible. Yeah, that's what I would think. If two select the correct statement of osmolarity. If two solutions are separated by selectively permeable from a high. No, that's the opposite. Is it per liter of solution? Wait. Oh yeah, that's right. Wait. I don't remember if that's true or not. Should we go back to the lecture? Did it close? I think it closed.
These processes, the activation, they need to tell you to it.
Oh wait.
Processes, so you can't be the same.
Include most marine invertebrates. The osmoregulators are. That's not right. The less the gradient between an animal's internal osmolarity and its external osmolarity, the higher the cost. That seems wrong. The less the gradient. Shouldn't it be easy to regulate if it's a small gradient? What does stenohaline mean again? I don't really. Yeah, this makes no sense. All marine invertebrates are still. All osmoconformers are marine animals. Okay. All right. Yeah, I guess that makes sense. It's not that all marine animals are osmoconformers, though. But all osmoconformers are. Okay. Select the correct statement describing the osmolarity of mammalian urine. Mammalian urine. I don't think that makes sense. I think it's A. I think it's this. You can't be a terrestrial osmo. Yeah, well, we just answered that, so then it has to be this. All the other stuff is non sequitur. Single-celled pyramecium live in pond water. Hypoosmotic. So if they're hyperosmotic, then they are going to have water flowing into them. Called contractile vacuole that enables them to osmoregulate. If sucrose or sodium chloride was added to pond water, at which final concentration I would assume that it's this. Because the bigger the difference, well, what does the contractile vacuole do? Which of the following best describes the role of transport epithelia in osmoregulation of marine fish? Wait. Of transport epithelia and osmoregulation of marine fish with bony skeletons. Excess salt for sure. Salmon eggs hatch in fresh water. The fish then migrate to the ocean, a hyperosmotic solution, and after several years of feeding and growing, return to the freshwater to breed. Which statement best explains how these organisms make transition from freshwater to ocean water and back to... Wait, I was under the impression that, like, that they only do the change once. How salmon do that thing where they get back to where they started makes no sense. Unlike most bony fishes, sharks maintain body fluids that are isoosmotic to seawater, so they are considered by many to be osmoconformers. Nonetheless, sharks osmoregulate at least partially. This sounds the most right to me. The body fluids of an osmoconformer would be iso... Birds, insects, and many reptiles excrete nitrogen in the form of uric acid, which reduces water loss, but requires more metabolic energy. Freshwater fish excrete nitrogenous waste as fish. Wait, hold on. Oh, it's just, yeah, it just diffuses as ammonia. Which answer best describes the formation of urea in mammals? Really? It forms in the liver? Which of the following is an advantage of excreting nitrogenous waste as urea rather than ammonia? Urea definitely looks toxic. Um, in animals, the catabolism of which molecules contributes most to the production of nitrogen? I think it's yeah. Um, as an appropriate group of animals to examine to observe Malpighian tubule would be. I'm pretty sure it's insects. Unlike in earthworms, Metanephria, and mammalian nephron. Well, that's definitely true. It's probably that. But I would also say this. Intimately associated with a capillary network. Oh, no, but an earthworm... An earthworm... No, it's probably this. Really? Because this one, I thought... Earthworms have a... Oh, this shows that I really don't know what the hell I'm talking about. Metanephrida... Oh, ciliated nephroderm draws in... Oh, yeah, it comes from the... Yeah, okay, so then it's probably this. Yeah. I guess what I was confused by is that... Yeah, okay. This just goes to show that I need to review that lecture, because I just watched it, and I don't know what the hell I'm talking about. It's definitely the coelomic fluid one, then. I need to draw some pictures of the excretory systems for sure. Materials are returned to the blood from the filtrate by which statement best describes the process of secretion? Which option correctly associates the mechanism for osmoregulation or nitrogen removal of the appropriate animal? That sounds right, actually. Uh... As a result of the non-selectivity of the mammalian kidney's filtration of small molecules, the kidneys have little control over blood.
Kidneys are bean-shaped paired organs that regulate water and electrolyte balance in terrestrial vertebrates. They also remove nitrogenous wastes, usually in the form of urea, from the blood and eliminate them in the urine. The renal artery and renal vein are large blood vessels that carry blood to and from each kidney. The ureter is a long tube that transports the urine formed in the kidney to the bladder for storage prior to excretion. The outer region of the kidney is called the cortex, and the inner region is called the medulla. The nephron is a basic functional unit of the kidney. Nephrons perform the work required to maintain water and electrolyte balance. Most nephrons are located in the cortex, but some extend into the medulla. Each nephron is made up of 5 regions, each performing a different function. 1. Urine formation begins in the renal corpuscle, which filters the blood. 2. The proximal tubule actively reabsorbs electrolytes, nutrients, and water. 2/3 of the electrolytes and water filtered from the blood is returned to the blood through the proximal tubule. 3. The loop of Henle creates a steep osmotic gradient by reabsorbing water and electrolytes differentially along its U-shaped length. This gradient allows the kidney to concentrate urine. A network of blood vessels supplies the loop of Henle. The vessels return water and electrolytes to the blood without disrupting the osmotic gradient. 4. The distal tubule, like some other regions of the nephron, reabsorbs electrolytes and water, but its activity depends on the body's state of hydration and is under hormonal control. 5. Urine formation ends in the collecting duct, where more water may be reabsorbed. The collecting duct is also under hormonal control. We'll use this simplified and flattened image of a nephron to describe the functions of each of its 5 regions. The first stage of urine formation begins in the renal corpuscle with the filtration of blood. Blood entering the renal corpuscle flows into a cluster of capillaries called the glomerulus. The structure around the glomerulus is called Bowman's capsule. The glomerular capillaries have pores and are surrounded by cells with slits. These features allow molecules and ions to be filtered from the blood based on their size. The high pressure inside the capillaries pushes water and small solutes out of the pores and slits and into the surrounding capsule, where the pressure is lower. Large components, such as proteins and cells, cannot fit through the pores and slits and remain in the blood, never entering the nephron. The resulting filtrate exits the renal corpuscle. The filtrate formed in the renal corpuscle contains waste products as well as valuable nutrients, electrolytes, and water. This filtrate enters the proximal tubule, where many of the valuable substances are reabsorbed. The epithelium of the proximal tubule has microvilli, which increase the surface area available for reabsorption. Intracellular sodium is actively transported out of the cells lining the tubule, a process that uses ATP. This pumping creates a sodium ion gradient favoring the entry of sodium ions into the cell from the lumen. Sodium moves through co-transporters, which use the sodium gradient to co-transport nutrients, such as glucose, vitamins, and chloride ions, from the proximal tubule into the epithelial cell. The movement of sodium down its concentration gradient provides the energy to move the other solutes against their concentration gradients. Water follows by osmosis. The reabsorbed electrolytes, nutrients, and water enter blood vessels near the tubule and are returned to the body. 2/3 of the water and sodium chloride filtered by the renal corpuscle is returned to the body via the proximal tubule. The osmolarity of the remaining filtrate in the proximal tubule is unchanged, however, because water reabsorption is proportional to solute reabsorption. The filtrate that emerges from the proximal tubule is relatively high in wastes and low in nutrients, and it is greatly reduced in volume. This fluid enters the loop of Henle. The loop of Henle sets up a steep osmotic gradient in itself and in the surrounding tissue. The osmolarity of the filtrate inside the loop is low in the cortex and high in the medulla, and this gradient is mirrored in the surrounding tissue. The loop of Henle functions as a countercurrent exchanger. The term countercurrent refers to the flow of filtrate in opposite directions in the two limbs of the loop of Henle. The osmotic gradient would disappear if the filtrates in these adjacent tubes ran the same way. There could be no exchange of water and solutes with the surrounding tissue. Water and solutes move through the loop of Henle in the following way. The descending limb of the loop is highly permeable to water, but impermeable to solutes. Water is lost by osmosis as it moves from a region of lower solute concentration inside the tubule to a region of higher solute concentration in the surrounding tissue. The fluid inside the tubule therefore becomes more concentrated as it flows deeper into the medulla. After the fluid rounds the bend, it enters the thin ascending limb, which is highly permeable to sodium and chloride ions and moderately permeable to urea. These solutes exit passively, following their concentration gradients. This part of the loop is impermeable to water, however. In the thick ascending limb, sodium and chloride ions are actively pumped out of the tubule. Therefore, as the fluid moves up the tubule, it again becomes less concentrated. The loop of Henle is an example of a positive feedback system, in which the product of a process causes the process to occur more. The positive feedback works like this. 1. The thick ascending limb pumps solutes into the surrounding tissue. 2. The high concentration of solutes in the surrounding tissue causes water to exit the descending limb by osmosis, leaving a hypertonic fluid inside the tubule. 3. This hypertonic fluid then loses solutes passively to the surrounding tissue, thus completing the positive feedback loop. What happens to the water and salt that move out of the loop? They quickly diffuse into a blood vessel that runs along the loop and returns the water and salt to the rest of the body. This return is especially important for the water that diffuses out of the descending loop, which would otherwise dilute the solutes in the kidney. The processes that we have discussed so far, filtration, reabsorption, and the establishment of an osmotic gradient, are for the most part not subject to hormonal regulation. The major solutes in the filtrate that exits the loop of Henle are urea and other wastes, and this fluid is fairly constant in composition over time. The filtrate then enters the distal tubule, where electrolytes and water are reabsorbed. Hormones control the amount of electrolytes and water reabsorbed by this part of the kidney. Hormones also control the concentration of the resulting urine within the collecting duct. If sodium levels in the blood are low, the hormone aldosterone is released. Aldosterone stimulates the reabsorption of sodium and chloride from the distal tubule into the surrounding tissue. Water follows by osmosis, thus decreasing the volume of water in the urine. Under conditions of dehydration, antidiuretic hormone, or ADH, is released. ADH stimulates both the distal tubule and collecting duct to become highly permeable to water. Water is reabsorbed into the surrounding tissue rather than being lost as urine, thus decreasing the volume of water in the urine. Individuals with diabetes insipidus produce little or no ADH. In the absence of ADH, the distal tubule and collecting duct are relatively impermeable to water. The lack of ADH results in the formation of a copious amount of urine that is low in solutes. As a unit, the nephron is remarkably effective in regulating water and electrolyte balance and maintaining homeostasis.
I don't really get that loop of Henle. Like, if the urea is... Here, I think I need to see it. Well, okay, we'll get to it in the book, but let's just do this. Because I kind of want to just go read the book. I kind of want to just hop on my iPad and read the book, bruh. Which of the following statements is true about... the kidneys are paired organs that remove nitrogenous waste from the urine. That's, like, super wrong. Most humans have one kidney. Yeah. The basic functional unit is the nephron. So we go to the corpuscle, the proximal tubule, then the distal, then the loop of Henle, then the distal. Actually, small distal. Loop of Henle. Loop of Henle. Which is the driving force for the filtration of blood by the renal corpuscle? I think it's this. Which regions of the nephron function independently of hormonal control? Oh shit. I think it's the corpuscle, the proximal tube, and the loop of Henle. In which region of the nephron is a steep osmotic gradient created? Which of the following statements best describes the actions of the hormone ADH? ADH causes... I think that. I think ADH, yeah. Oh shit, I'm done. I'm done. I'm done with my homework. Now we just gotta read like 5 chapters of this book. So, where did we leave off? Wait, is there one more lecture that I need to do? I guess I need to do this one. Okay, I think I know what's gonna happen. Just gonna go lie down and read. But, I guess I'm not gonna take notes yet. The renal corpuscle.
Keep your eyes on this. This starfish is digesting its meal outside its own body. Starfish have a truly bizarre way of eating. External digestion. When they catch prey too big to swallow, they push their stomachs out through their ventral mouths and wrap them around their victim. Their powerful digestive enzymes then break down the prey into a soupy, nutrient-rich mush that the starfish slowly absorbs. After about 8 hours, they pull their stomach back inside to finish digestion. Weird? Absolutely.
So we left off last time introducing the nephron as the basic unit of the vertebral kidney, as this association then, the structure of a tubule in close association with capillary beds, our cardiovascular system. And that the basic functions, like of all excretory systems, both for removing metabolic wastes and for osmoregulation, volume regulation of fluids, all the things that kidneys do. We have the functions of filtration, where the nephron, it's the blood pressure that's pushing the plasma fluid across the walls of the glomerular capillaries into the Bowman's capsule. And so we are non-specifically filtering everything in the blood except the blood cells and proteins and anything that's being attached to proteins. So that's the filtration step. The reabsorption step is a lot of those things that got filtered we need to keep, so we need to take them back into the circulatory system. That's reabsorption. And then some things we need to get rid of even faster than that fraction that's been secreted. And so secretion then, those filtered rather, so we need to secrete them to get rid of them even faster than that. So the overall net result of most excretory systems then is this balance, that the more of something you filter, the more of something you secrete, the more of it you're going to excrete and remove from your body through your excretions. Whereas the more you reabsorb something that you did filter, then the less you're going to excrete it. And in fact, any things that are filtered, we can reabsorb 100%. So even though they're filtered, we don't lose them. So of these nephrons then, these tubule systems in close association with our circulatory system, each of your kidneys has about 1 million of them. So we've got a lot of these things working hard. And so again, looking at the overall general structure of a kidney, kidney is again located in the upper part of your abdominal cavity, in the dorsal region of it, so towards the back, which is why in poetry, in old poetry, whereas your heart, which was shallow and often you could tell it beating faster, was your shallow emotions, the kidney, because it was deeper in, represented your deeper emotions. So poetry aspect to knowing kidneys. But the structure of the kidney, we can see the blood vessels coming into this side here called the renal pelvis. So renal having to do with the kidney. And then the outer part of the kidney being the renal cortex, the inner part being the renal medulla. And so here there's diagrammatically a little section here where one of those nephrons is located. So here we can see all this vascular system out here in the cortex, and then the tubule region, which extends from the cortex down through the medulla to the renal pelvis. So we'll use our own kidneys as a model of most vertebrate kidneys and mammalian kidneys in particular. So again, we have a pair of them located up here in the rear part of your thoracic cavity. And of course, since these are processing your bodily fluids, our bodily fluids have to be made accessible to them. So a tremendous amount of your blood flow does go through your kidneys. About 20% of your systemic blood circulation travels through your kidneys. And so the urine from that over 1 million nephrons converges into that renal pelvis region. From the renal pelvis, a tubule extends, or a tube in this case, called the ureter. And so each kidney has its own ureter that then collects on the urinary bladder. And the urinary bladder then connects via the urethra to an opening to the outside world to excrete those wastes. So again, all blood travels through your kidney about 200 to 300 times a day. It's got the highest blood flow and the highest metabolic rate because there's a whole lot of active transport going on in here for a gram of any tissue in your body. So it's important what it does. It's expensive what it does. So we said we have a tubule component and a vascular component. Let's first look at the tubule components. So the filtration step happens at this little balloon at the end of the tubule. So it's a blind balloon that then pockets inward. So it's like if you have a balloon and pocket it inward, that pocket then is called the Bowman's capsule. So that's where the filtration, so that's where our first capillary bed is going to insert itself and the filtration step is happening. From the Bowman's capsule, the tubule then goes through this twisty region, convoluted region, that's close to the glomerulus. So that's called the proximal. Proximal means close, convoluted, twisty tubule. So the proximal convoluted tubule is the next region that comes off the Bowman's capsule. From there, the tubule does this little dip down into the medulla region and back up. That's called the loop of Henle. Then we go to another little twisty region. So another convoluted tubule, but this is far away. So the word is distal. So proximal, close convoluted tubule, distal, the far convoluted tubule. So on both ends of the loop of Henle, we've got these twisty regions of convoluted tubule. Then, so that's one nephron. Multiple nephrons then plug into one collecting duct. So the next part of the tubule system is a collecting duct. So all these little branches here represent multiple nephrons that are all plugging into one common collecting duct. You'll have thousands of these collecting ducts, but we have multiple tubules condensing on them. Okay, so that's the tubule components of a nephron. The vascular components then goes from our renal artery, and renal means kidney, to an arteriole, to our first capillary bed. So that's the afferent arteriole, afferent before. Then our capillary bed where filtration is happening is called the glomerulus. So the glomerulus, a structurally unique capillary bed that allows for filtration to occur. Then from the glomerulus, we go to a second arteriole. The efferent arteriole. Remember, A comes before E, A is before the glomerulus, efferent is after the glomerulus. And from the efferent arteriole, we go to our second capillary bed in series. So two capillary beds in series in the same vascular system here, called the peritubular capillary bed, peri around the tubules. So here's where our reabsorption and secretion steps are going to occur. Now, in some nephrons, this peritubular capillary bed goes down deep into the medulla. And that special peritubular capillary bed that's down in the medulla is called the vasa recta. So the vasa recta is a subset then of the peritubular capillary system. Okay, so that's the vascular component of our nephron. So tubules and blood vessels. So sort of a preview then of how all this is going to work is that so we have the glomerulus within the Bowman's capsule. That's called the renal corpuscle. So the renal corpuscle is where the filtration step is happening, where the blood is being filtered non-specifically into the tubule. And so we call that, because we have filtration under pressure, that's called an ultrafiltrate. So the ultrafiltrate is that portion of the blood plasma that's not on proteins that's filtered non-specifically into the tubule. So from the renal corpuscle then, that's where our ultrafiltration is occurring. So fluid, both water and solutes, are being filtered non-specifically into the tubule. Then in the proximal tubule, this is where we're going to reabsorb about 2/3 of the volume of the filtrate. So we need to get a lot of that back. So most of the water, most of the salt, and under normal conditions, all of the circulating energy substrates. So your blood sugar, your amino acids, your water-soluble vitamins, all those things got filtered, but we don't want to lose them. So under normal conditions, we get 100% of them back, right, immediately in the proximal convoluted tubule. So they didn't spend a whole lot of time in the tubule. Then the loop of Henle, we have our descending loop, so descending going down, where we reabsorb more water, and our ascending loop where we reabsorb more salt. So again, osmoregulation, very important part of the kidney. Then our distal tubule, we can reabsorb more salt, and this is where a lot of our secretion. So secretion is happening in both convoluted tubule regions. So here, there are other things that have been marked, often by the liver, things that are in your circulation that you want to get rid of, and so the lining of those blood vessels recognize those things and secretes them, so actively transports them into the tubules. And I can get rid of them even faster. And the collecting duct primarily is getting back even more water, right? Because you got to get that water back. Okay. And you may notice also that pH regulation is another function of the kidney. So the kidney also, in both convoluted tubule regions, can reabsorb bicarbonate, your main blood buffer, and can secrete or get rid of acid, hydrogen ions. So the kidney is also involved in pH regulation of your bodily fluids. Okay, so that's kind of a preview. Let's now go into a little more of the details. So as we said, the filtration step is nonspecific, and it's happening in the Bowman's capsule, the tight association of the glomerulus of the cardiovascular system and the Bowman's capsule of the tubule. So ultrafiltration, so flow from the hydrostatic pressure of the blood. So the blood pressure is pushing fluid across the walls of these capillaries. Okay. Now, to make sure this happens fairly rapidly, because we need to process a whole lot of fluids here, the capillary beds are actually fenestrated. Meaning there's actually little gaps between the adjacent cells. So usually we think of an epithelial tissue of not having any gaps, but there's tiny little gaps here that allows tiny things to percolate through there without having to cross cell membranes. That's why it's nonspecific. We can leave the blood without crossing cell membrane. So if you're, again, a cell or a protein, you're too big and too charged to penetrate through those things. But otherwise, all your other solutes are passing nonspecifically. Then the tubule cells are podocytes, like we talked about in a lot of other filtration systems of the metanephridia of earthworms and mollusks, for example. We talked about having those slits. Even in the protonephridial system of flatworms, we talked about having this interdigitation of adjacent cells that creates these filtration slits. And so we have both filtration through these little pores and fenestrated capillaries and these filtration slits in the tubule cells. So again, from the blood, we're going through this little tiny space between the capillaries, through these tiny little spaces between these extensions of the cells. And so it's nonspecific. Again, you're not crossing cell membranes, but it's relatively fast as opposed to just diffusion, right? So it's under pressure, so it's leaking relatively quickly. So fluid may pass between cells instead of through them. So it's rapid and non-selective. So what are in all non-colloidal solutes? So colloids are big things like proteins. So all your solutes that aren't big like a protein is now the ultrafiltrate that's being filtered into the lumen of the tubule. Okay. So this is just another illustration trying to just diagram the same sort of thing. So again, this is from the tubule side looking towards the capillary. You can see all these podocytes, all their little tiny little protrusions here that are overlapping to create these filtration slits. So the filter then are these fenestrated capillary endothelium, and It's also acting as part of the filter. Okay, so we're filtering from the blood into the tubule. So the rate at which fluid is being filtered by all the glomeruli in both your kidneys is called your glomerular filtration rate. So the volume of filtrate produced by both kidneys per minute. And so that's typically about 120 mils per minute. Right? That's a pretty good rate. A little bit less in women, a little bit more in men, but about 120 mils. Okay, so of the blood flowing into from the afferent arteriole, then, again, all the proteins and all the cells are just continuing on to the efferent arteriole, but 120 mils per minute of the water and all the rest of the solutes are being filtered. Okay, that's the glomerular filtration rate. So again, get these numbers straight of what we're talking about. So all that blood that's flowing to the kidneys, which is this huge amount of blood, then only 55% of that is plasma, right? 45% of it's red blood cells, and remembering from our circulation lecture. Then of that 55% of the blood that is traveling through the vessel, about 20% of that volume is filtered. 80% of it continues on, right? So these efferent arteriole is not dry, right? So that 80% of the volume that came in to the glomerulus. So of whatever flowed into the glomerulus, 80% of that volume continues on. It's 20% of the volume is filtered. Okay? But that's a huge amount. So 20% of the plasma that enters the glomerulus is filtered into the nephron. So that adds up to about 180 liters of fluid filtered by your kidneys a day. Okay, so tremendous volume flowing through this filtration system. Now, obviously, we can't afford to lose 180 liters of fluid a day, right? That would pee you dry in about 20 minutes. So we need to get almost all of that back. So somehow we need to get over 99% of that volume back. Okay, so typically, even though our kidneys filter 180 liters a day, under normal hydration conditions, we're only producing 1.5 liters of urine a day. Okay, so over 99% of it we've gotten back. Now we can reduce that if we're dehydrated, need to hold on to more water. We'll talk about how that is, but we do need to use some, because remember, that's one of the issues of having a water-soluble waste product is we need water to wash it away. And so we have what's called a obligatory water loss then of about 400 mils a day that we need to lose just to flush the waste away. Okay, so typically we lose a liter and a half. If we're really dehydrated, we can reduce that down to 400, so 0.4 liters a day. But again, at 180 liters filtered, only losing 0.4, that's a pretty efficient system. Okay, so that's the filtration. So now we've created our ultrafiltrate in our tubule. Now we need to start working on getting things back that we need. So letting things go that we want to go, getting back the things we want. Okay, so again, the rationale, if you will, behind the system is there's all kinds of possible toxins that could have been introduced in your body somehow. You don't need a list of anything that could be a toxin. You just need a list of things you need to keep. And everything that's not on the list is going to be excreted. So get back what you want. Everything that's left is considered waste. And so we come into that close twisty region, that proximal convoluted tubule region. So in this proximal convoluted tubule region, we're going to start getting things back. And since our major solute in our blood plasma, and therefore the major solute in the tubule, is sodium chloride. So that's the main thing we need to work on getting back. So here we have active transport of sodium. Chloride follows passively. So this is opposite of what we talked about in the fish scale. In the fish scale, we actively reabsorb the chloride, and then the positive charges of sodium follow the chloride. In the kidneys, the other way around, we're actively reabsorbing the sodium, and now the negative charge of the chloride is following the positive charge of the sodium. Okay, so we're actively reabsorbing the sodium. So the cells lining the tubule here are actively removing sodium from the filtrate and putting them back into the peritubular capillaries, back into the circulation. Chloride is following passively. Now there's a whole bunch of aquaporins. Remember, aquaporins, the proteins that allow facilitated diffusion of water. So water can permeate across these membranes rapidly. So as fast as we remove solutes, water is going to follow it. So the net result is, by the time we go through all this twisty region of the proximal tubule, we've reabsorbed about 65% of the sodium, 65% of the chloride, and 65% of the water. Right? So because we're absorbing water and solutes evenly, the osmolality doesn't change. So the fluid's reduced about 1/3 of its original volume. Right? If we reabsorb 2/3 of it, then 1/3 of it's left. So everything that we didn't reabsorb is now 3 times as concentrated as when we filtered it. Right? It's in 1/3 the volume. But even though we reabsorbed that volume, it's still isosmotic because we absorb water and solutes at the same rate. And remember, isosmotic, that we said that most bodily fluids in vertebrates is about 0.3 osmolar, right? Or another way of saying 0.3 osmolar is 300 milliosmolar, right? Milliosmolar, thousandths of a osmolar, right? So 0.3 times 1,000 is 300. So it's another way of saying the same thing. Typically, we'll be using these milliosmolar units as we discuss what's going on here. Okay, so 300 milliosmolar is isosmotic, meaning the same concentration as your blood and your other bodily fluids. Okay, so we got back to 2/3 of the volume and not change the osmolality. Now, remember we said that in the proximal tubule is also where we get 100% of those energy substrates. And so to do that, we use active transcellular co-transport. Sounds like a lot, but we've talked about this before. Okay, so we're using that sodium gradient. Again, remember, sodium and chloride are the major solutes. So when you move huge numbers of those ions, you can piggyback movement of other things that are in smaller concentrations. So here's our mechanism of how that works. So here, where all these little protrusions are, right, looks kind of like the lining of your intestines with all these little microvilli, giving you lots of surface area. And then, so that's the apical membrane, is the membrane of the cell facing the lumen of the tubule. The other side is the basal membrane, right, and lateral is on the sides. So in this apical membrane, well, let's actually start with the basal membrane. The basal membrane is where the major active transporter in animals occurs. So in plants, in fungi, in bacteria, we said the major transporter was the proton pump, hydrogen ion pump. In animals, it's the sodium-potassium pump. So this is constantly working in every cell in your body, where you're constantly using ATP to pump sodium out and potassium in. So your concentration of sodium inside the cell is very low. Okay, so pumping sodium out, which is then going into the bloodstream. Now, because the sodium concentration in the cell is so low, it's got a really high concentration gradient to pull sodium in out of the filtrate. And so we've got facilitated transporters in the apical membrane. So active transporters in the basal membrane, facilitated transporters in the apical membrane. But instead of just allowing sodium to flow through for the sake of sodium, most of these transporters are co-transporters, meaning that they use the flow of sodium to drive the pulling in of something else, in this case, a glucose transporter. So because you created this huge sodium gradient, the sodium flowing through that transporter powers pulling in of glucose. Okay, so this is indirect active transport, right? We spent the ATP on the sodium potassium pump, but that gradient we created with the sodium potassium pump is driving the movement of sodium and therefore the movement of glucose. So active co-transport, indirect transport. Now, because we're forcing glucose in the cell by this co-transport, concentration of glucose is high. You have glucose facilitated transporters in the basal membrane. Glucose follows this concentration gradient out of the cell and into the blood. So active transcellular co-transport. The active part's here. The transcellular part is going from the lumen of the duct across the cell, transcellular, into the blood. And since there's so much sodium traveling across here, we can have different co-transporters for glucose, for amino acids, for your water-soluble vitamins, all those things where we can, bicarbonate, we can use this flow of sodium to power all of this because we have different co-transporters for all these different mechanisms. So normally 100% of glucose, 100% of amino acids, of your water-soluble vitamins, of your bicarbonate, those things you need to keep in your blood, even though you filtered them, you want to keep them. We reabsorb 100% of them in the proximal tubule. Okay. Okay, so now we've got, again, 1/3 the volume, but the same osmolality, so we're still 300 milliosmolar isotonic because we reabsorb water and solutes at the same rate. We've got all our nutrients back. But now we have to primarily work on getting rid of more wastes and osmoregulation. So now we go into loop of Henle. So loop of Henle, as we said, we're going to dip down into the medulla and back up. And this position of the descending and ascending limbs drives each other. So this is called a countercurrent multiplier. So we've talked about countercurrent exchangers before, but this is a countercurrent multiplier. So this is different, other than we have flow going one way down and one way up in close proximity. So that's the countercurrent part. So that's the same. But now it's what's happening in one is driving what's happening in the other. Okay, and we'll try to describe what I just said. So even though we go through the descending limb first, let's talk about the ascending limb because that's what drives the process. So if you look here in our diagram, we can see that when we go into the loop of Henle, we have this thin tubule. And then as we come up, we come into this thick tubule. So this is called the thick segment of the ascending limb. And the thick segment of the ascending limb is impermeable to water. So water cannot transfer here, but it's got active transport of sodium chloride. So again, direct active transport of sodium, co-transport then, co-transport of chloride. Okay, so we're actively reabsorbing sodium and water can't and chloride, and water can't cross. So because we're removing solute and not water, the concentration is going down. Okay, so in the ascending limb, the osmolality of the filtrate in the tubule is decreasing, right? So we call that dilution. Going down. Okay, so in the ascending limb, the osmolality of the filtrate in the tubule is decreasing, right? So we call that dilution, but it's not dilution because we're adding water. It's dilution because we're removing solutes. Okay, so by the time we actually come out of the ascending limb, we're at a lower osmolality than when we started. But since we're pumping this salt out into the interstitial fluid of the cells of the medulla, it's increasing the osmolarity of the medulla, right? So the filtrate's becoming less concentrated. The tissues around the tubule is becoming more concentrated, right? Because we're taking solutes from the filtrate and putting it into the tissue. Okay, so that's the ascending limb. The descending limb is the other way around. It's permeable to water. It's got aquaporins in it, so it's very permeable to water, but it's not permeable to salt. right? If you don't have the transporter proteins for an ion, they're not going to cross the membrane. So the sodium chloride that's out here can't get in because it's not permeable to salt. But now because you've got this high concentration of salt in the tissues outside, that's pulling water out of the tubule. So this is dehydrating it, right? We're removing water osmotically. And so the water is coming out of the descending limb and back into the circulation. And so you can see the concentration is increasing because we're removing water, not solutes. So that's why we say it's countercurrent multiplier, because here, where we're putting out less salt, there's less water that has to come. You get down here, it's more and more concentrated, so you need to be near a more concentrated region over here to continue to pour water out by its osmotic gradient. So in the descending limb, the ascending limb is driving the descending limb, we're now increasing the osmolality of the filtrate because we're removing water and decreasing the volume of the filtrate, right? Because most of the volume of the filtrate is water. So if you're moving water, you're decreasing the volume, right? So it's the water that's determining the volume. Moving water, volume's decreasing. Okay, so in the descending limb, then we're decreasing in volume. In the ascending limb, we're decreasing in osmolality. Okay, so the ascending limb is driving what's going on in the descending limb. Now, in this thin region of the ascending limb, this is still permeable to water, but the concentration now is so high that now the salt wants to leave. So actually here we get passive loss of salt because the concentration of solute inside is so high because we remove so much water that now all of a sudden we open up some sodium gates and the salt's diffusing out passively. Whereas you get up here, now it's starting to be more dilute. Now we have to switch to active transport of salt. So in the ascending limb, we have both first passive and then active transport of salt. Okay, so that was our countercurrent multiplier. Now we also have a countercurrent exchange system. That's how we get it back into the circulation. So that's how we got water and salt out of the tubule, into the tissues around the tubule, but we need to get that back into the circulation. And so we have a countercurrent exchanger between the peritubular capillaries and the tubule in the loop of Henle. So whereas the loop of Henle, we're going descending here and ascending there, with the vasa recta, remember that part of the peritubular capillaries that runs deep in the medulla, the descending limb is parallel to the ascending limb of the loop of Henle. The ascending limb of the vasa recta is next to the descending limb of the loop of Henle. So those are countercurrent to each other. So the peritubular capillary flow is countercurrent to the tubular flow. So in the blood that's first coming off is descending here, where we have a very dilute osmolality here. So when you have the most dilute blood, right, coming off of the circulation, we have the most dilute here, but that's where we're actively transporting out sodium. So that's where we're absorbing sodium into the circulation. Now we're coming up this way, and now we have the water gradient coming out of the tubule and into the circulation. So on the descending vessel, we're collecting sodium and chloride. The osmolality of the plasma is going up. On the ascending vessel, now we're collecting water. The osmolality is coming down, but the volume's going up because we're collecting water. So by the time we come back up and go into the renal venule, we've collected a whole bunch of vessels where it's a current exchange system. That's how we get it back into the circulation. So that's how we got water and salt out of the tubule, into the tissues around the tubule, but we need to get that back into the circulation. And so we have a countercurrent exchanger between the peritubular capillaries and the tubule in the loop of Henle. So whereas the loop of Henle, we're going descending here and ascending there, with the vasa recta, remember that part of the peritubular capillaries that runs deep in the medulla, the descending limb is parallel to the ascending limb of the loop of Henle. The ascending limb of the vasa recta is next to the descending limb of the loop of Henle. So those are countercurrent to each other. So the peritubular capillary flow is countercurrent to the tubular flow. So in the blood that's first coming off is descending here, where we have a very dilute osmolality here. So when you have the most dilute blood, right, coming off of the circulation, we have the most dilute here, but that's where we're actively transporting out sodium. So that's where we're absorbing sodium into the circulation. Now we're coming up this way, and now we have the water gradient coming out of the tubule and into the circulation. So on the descending vessel, we're collecting sodium and chloride. The osmolality of the plasma is going up. On the ascending vessel, now we're collecting water. The osmolality is coming down, but the volume's going up because we're collecting water. So by the time we come back up and go into the renal venule, we've collected a whole bunch of volume of water and salt, but the osmolality is back to isosmotic. We're back to 300. Right? So we went a lot higher than 300 on the way down, and then back to 300 on the way back up. Right? So we're picking up volume of salt and water as we go down and back up. So countercurrent exchange between the tubule system and the cardiovascular system. So the result of this, that between the proximal tubule, where we got 65% of it back, we've now gained another, 35% of it back. And now we've got 90% of the salt back and 85% of the water back. Okay, so again, we got more salt than water. That's why we were now hypotonic when we came back up, because we took back more salt than water. So it's now lower concentration than when we started, but much less volume. We're only 15% of the volume that we started with when we filtered it. Okay, so anything that was filtered and not reabsorbed is now going to be in 15% of the original volume. It's going to be 7 times more concentrated than when you filtered it. Okay, so we're concentrating those wastes more and more and more just by reabsorbing the water that they were filtered in. So the result of the loop of Henle then is, of course, to get back this huge volume of water and salt back into your circulation, but it's also created this gradient of osmolality in the medulla of the kidney. So again, out in the outer cortex, it's all isotonic, right? You're still at 300 millimosmolar in the tubule, in the blood, in the tissues, it's all at 300. Whereas as you go deeper down into the medulla, where that loop has been dumping more and more and more salt, now it gets saltier and saltier and saltier and saltier. So again, we're going from close to isotonic, right at the outer medulla, down to 1200, sometimes even 1400 milliosmolar, down in deeper in the medulla. Okay, so part of the function of the loop of Henle is to increase the osmolality of the interstitial fluid of the medulla. We'll talk about why that's important. Okay, but from the loop of Henle, we now go into the far twisty region, the distal convoluted tubule. And the distal convoluted tubule, we continue to reabsorb more sodium chloride, so that by the time we go to the distal tubule and then that plugs into the collecting duct, so the cortical region of the collecting duct physiologically is the same as the distal convoluted tubule. And so we're continuing to absorb more and more salt until we get 98 to 100% of it. So either almost or all of the salt that was originally filtered is now reabsorbed back into circulation. Now, what's the difference between 98 and 100? Considering the volume of salt that we filtered, 98 and 100% is actually a significant difference. That's regulated by the hormone aldosterone. So aldosterone is a steroid hormone. We'll talk a little bit more about it later. That says that reabsorb more salt. So without aldosterone, you reabsorb 98% of your salt. With aldosterone, you increase that until you can effectively reabsorb all of it if you really need to. So here's where we're regulating our salt reabsorption. Are you going to reabsorb 98% of it and let 2% of it go because we have plenty of salt? Or do we need to keep our salt and reabsorb all of it? Of course, it's the amount of aldosterone tells you where within 98 to 100% you're going to be. So it's not 98 or 100, somewhere between 98 and 100. Okay, so we said then, that's kind of summary then, that as a result of our loop of Henle, that we reabsorbed water in the descending limb, salt in the ascending limb, and created this osmolality gradient in the medulla. Now all these nephrons are plugging into a collecting duct, and that collecting duct is going back through that medulla again. That's going to create the osmotic gradient to reabsorb more water. Because, yeah, we reabsorbed like 98% of it, but we need more than 99% of it. We need more. And so it's by going through this region here that we can reabsorb more water, and therefore really concentrate what we're getting rid of and lose less water. Now, this is another part of the system that's regulated. So we talked about all the stuff that's automatically happening. Then we said, okay, aldosterone regulates how much of the salt we reabsorb. We now going to regulate how much of the water we reabsorb. If we're overhydrated, we need to dump water. If we're dehydrated, we need to hold on to water. Where within that spectrum are we going to be? And that's regulated by another hormone. This is not a steroid hormone, it's a peptide hormone called antidiuretic hormone. Right? So a diuretic is something that makes you pee more. So an antidiuretic makes you pee less. And the way this works, so as we're traveling through the medulla of the kidney, remember the things that affect the fusion rate: the size of the concentration gradient and the permeability of the membrane. How fast can it go? So we've created this concentration gradient because of the loop of Henle. So the thing we can regulate is how permeable is the membrane. And that's what ADH does. ADH tells the cells that are lining the collecting duct to add more aquaporins. And the more aquaporins you do, then more water is going to be reabsorbed. By the time the filtrate travels from the cortex to the renal pelvis, how much time did you have to lose water, and therefore how much how fast is water leaving. So the faster water is leaving, the less water is going to be still there by the time you get to the renal pelvis. So ADH then regulates how many aquaporins are in the tubular membranes of the collecting duct. Now it also affects, because now remember we've absorbed either almost all or all of the sodium chloride, so they're no longer the major solute. The major solute now is urea, or nitrogenous waste. So the urea is now really concentrated because we're in probably 1/10 the volume, so it's 10 times more concentrated than it was in the blood. So we have a concentration gradient of urea wanting to get out. And ADH can also then tell the cells to add urea transporters. Now, why would urea is a waste product? Aren't we supposed to getting rid of that? Well, if you really need to hold on to water, it's more important to hold on to water than to get rid of all the urea. So ADH will also cause, under conditions where you really need to absorb more water, in the deep inner part of the medulla in particular, to add urea transporters, therefore allowing urea to facilitate diffusion out of the tubule, and therefore bring more water with it. Right? You're increasing the osmolality even greater now, and water is going to follow it. So we're increasing the concentration gradient of water, as well as increasing the permeability of the membrane to water. Now notice it also actually opens up urea transporters in the ascending limb of Lupus-Henle. But the concentration gradient is such that it's, because we've removed so much water, is higher in the collecting duct than in the loop, so it diffuses back into the loop. So in that thin segment of the loop, urea can diffuse back into there. So we actually have a cycle where urea is leaving the collecting duct into the loop, traveling back up the proximal tubule, back into the collecting duct, and it just kind of cycles around and around and around. So we're not really putting it back in the circulation. We're just using it to increase the osmolality of the inner medulla. Okay, now most of it's going to continue on and we're eliminating it, but some of it's allowed to recycle to maintain that concentration gradient to make it even more efficient at reabsorbing water. Okay, so ADH affects how much water we're going to reabsorb and therefore keep in our body by regulating both aquaporins and urea transporters. So there are actually several different aquaporins that the body makes, and the kidney in particular makes. So again, different genes that are making different versions of these proteins that are allowing water to cross that lipid membrane. So again, these aren't holes, there's water-specific transporters. So this is a structural model of one of them. So here's the from the tubule side into the cytoplasm of the cell, and the water is traveling in single file as it actually binds and lets go of these water molecules. That's a lot faster than trying to diffuse through that lipid membrane. And so we can see these four versions of aquaporins that the kidney makes. So aquaporin 1 is constitutive, means that it's always made, and that's in the proximal tubules, the descending loop of Henle, and the vasa recta, right? So that automatic part of water reabsorption in the proximal tubule, where we got 2/3 of the water back, the descending loop of Henle, where we got up to 90% of it back, and then the vasa recta, getting that reabsorbed water back into the blood vessels. So that's aquaporin 1, that's always there. Aquaporin 2 and 3 are the ones that are ADH dependent. And so aquaporin 2 is in the apical membrane of the collecting duct, aquaporin 3 in the basal membrane of the collecting duct. So one side or the other. And then there's aquaporin 4 that's always in the basal membrane, but that's constitutive. Okay, so these are the two that are being regulated by ADH. So if we look at the regulation then, that if in cases where we will have normal hydration and we don't need to reabsorb more water from the kidney, and we can just kind of let it go, except for what little percolates by slow diffusion, simple diffusion across the membrane, then we can have, so here's our aquaporin 3s that we've constitutively laid down in the basal and different genes that are making different versions of these proteins that are allowing water to cross that lipid membrane. So again, these aren't holes, there's water-specific transporters. So this is a structural model of one of them. So here's the from the tubule side into the cytoplasm of the cell, and the water is traveling in single file as it actually binds and lets go of these water molecules. That's a lot faster than trying to diffuse through that lipid membrane. And so we can see these four versions of aquaporins that the kidney makes. So aquaporin 1 is constitutive, means that it's always made, and that's in the proximal tubules, the descending loop of Henle, and the vasa recta, right? So that automatic part of water reabsorption in the proximal tubule, where we got 2/3 of the water back, the descending loop of Henle, where we got up to 90% of it back, and then the vasa recta, getting that reabsorbed water back into the blood vessels. So that's aquaporin 1, that's always there. Aquaporin 2 and 3 are the ones that are ADH dependent. And so aquaporin 2 is in the apical membrane of the collecting duct, aquaporin 3 in the basal membrane of the collecting duct. So one side or the other. And then there's aquaporin 4 that's always in the basal membrane, but that's constitutive. Okay, so these are the two that are being regulated by ADH. So if we look at the regulation then, that if in case is where we will have normal hydration and we don't need to reabsorb more water from the kidney, and we can just kind of let it go, except for what little percolates by slow diffusion, simple diffusion across the membrane. Then we can have, so here's our aquaporin 3s that we've constitutively laid down in the basal membrane, so the membrane facing the blood vessels, whereas the apical membrane facing the tubule doesn't have any aquaporins in it. So water is not going to have facilitated transport. It's only got simple diffusion. But we've made ahead of time, in case we need them, we made aquaporins and set them in vesicles, the membranes of these vesicles. So that's aquaporin 2s. Okay, so we made them ahead of time, because it takes a long time to make a protein. But we made them ahead of time so they're ready in case we need them. So now in the presence of ADH, which is also called vasopressin, that's another name for the same hormone, these vesicles fuse their membrane, the apical membrane. So they just added their membrane with their transporters in the membrane. Now you've got aquaporins. Now water can come in this side, and those aquaporins are already there, so it can go across the cell and have transcellular transport across the cell. So that's the fast response, is taking these transporters you've already made and simply inserting them. Whereas this long-term response, if you've been dehydrated for a long time, then you got to make more transporters. Like, okay, let's gear up and make more of both of these aquaporins and get them in the membranes. Okay, and this process is reversible too, that if you want to fast slow down, you can just take the spin membrane and remove it back into a vesicle. Okay, so fast responses, long-term responses, but both have to do with inserting and removing these transporter proteins into the membrane of the cell. Okay, so that's regulating the permeability of the lining of the tubules to water. So again, summarizing what we talked about then, the osmolarity of the interstitial fluids, that's the fluid around the cells or among the cells of the kidney itself. As you go deeper down, again, so the cortex is going to be isosmotic to the blood. The deeper down you go, the higher the osmolality becomes, both because of salt and urea. So because of salt first, and then your inner parts also because of urea. And so we can look at what's going on with the tubules. So we started isosmotic from the filtrate, which was the same as the blood. Then we reabsorb volume, but not changing the osmolality, because we reabsorb salt and water at the same rate. In the descending limb, we got more concentrated because we removed water and not solute. The ascending limb, we became more dilute because we removed solute and not water. So when we came up, we were lower in concentration than when we started, because the net result was we reabsorbed more salt than we did water. Then we traveled down the distal tubule, and what happens to the osmolality there depends on are we reabsorbing 98 or 100% of that salt. And so we go down the collecting duct, we're reabsorbing more water, and again, in that outer region, it's acting like the distal tubule, so aldosterone may tell you to reabsorb more salt there. But primarily, we're reabsorbing water. In the inner medulla, if you really need to have a big concentration gradient for water, we can also reabsorb more urea. And so the osmolality of the cortex, of the filtrate, can become close to at least isosmotic with the interstitial fluid. Okay, so again, red arrows are all active transport, blue is all passive transport. Water is always passive. Again, as we said before, the salt is passive in the thin segment of the ascending limb, active in the thick segment. Okay, and then over here, we've got the aldosterone regulated active transport. So the overall osmolality related to water, sodium chloride, and urea, our solvent and our major solutes. So coming back to this illustration then, and now how we understand what's going on with it. So of the blood plasma that entered in to the glomerulus, and 80% was filtered, 20% was filtered, 80% of it continued on. But that's still 120, 115, 125 mils per minute. We need to get over 99% of that back. So the 180 liters of fluid we're filtering every day, without ADH, we get back to 99.2% of it. And that's normal hydration, producing 1.5 liters of urine a day. Under severe dehydration, now we maximally produce ADH, and we get that up to 99.8%. Okay, so the regulation of water reabsorption is the difference between 99.2 and 99.8. That doesn't seem like much until you remember you're talking about a fraction of a percent of 180 liters a day. Now all of a sudden that's a big deal. So that's the difference between 1.5 liters of urine and 400 mils of urine. That obligatory water loss, that minimum amount we need just to flush out our metabolic waste. Okay, so we say over 99%, we mean 99.2 to 99.8. Okay, so our kidney then can regulate reabsorbing between 98 and 100% of the salt and 99.2 and 99.8% of the water. That way we're not peeing ourselves dry, but we're able to regulate the osmolality of our bodies. So this is just looking, again, at the changes in osmolality as you go through different regions, and the difference between when you're holding on to as much water, you've been dehydrated, you need to hold on to as much water as possible, as opposed to when you've been overhydrated and you need to dump water. So again, in the proximal tubule, no difference between those two, that's constitutive. That you reabsorb 2/3 of the volume, and you reabsorb water and salt at the same rate. So the osmolality, so this is the ratio of osmolality between the tissue fluid and the blood fluid, in other words, and the filtrate. I'm sorry, this is the tubule fluid, the filtrate, and the plasma. So that doesn't change. Then you go through the loop of Henle, and again, you become more concentrated on the way down, more dilute on the way up. So you end up with being more dilute than when you started, even though the volume was greatly less. And then we start getting into the more regulated regions. So in areas where we need to dump water because we've been drinking more water than we need, then we continue to reabsorb more salt, so it gets more dilute, but not reabsorb more water. And so the osmolality continues to be low compared to tissue. So we're dumping water faster than solutes. So our urine is now more dilute than the blood was. Whereas if we need to hold onto water because we're dehydrated. Now we start reabsorbing water faster and faster, so the solute concentration increases and then goes way up here where we're now much more concentrated than we were when we started. Okay, so again, regulating the salt and water reabsorption. This is the same graph only with adding the volumes in here. So again, if we start off with 125 mils a minute, so I guess this is